The night air above Kummersdorf was brittle with frost, the stars hard and cold as the metal domes of the test range. Inside Building 7, beneath the yellow glow of acetylene lamps, a group of German engineers huddled around a workbench. It was the evening of January 21st, 1945. Soviet artillery could already be heard in the far distance, a dull thunder rolling across the Oder. Yet here the men spoke in hushed technical German, as if the war were still a laboratory problem to be solved. On the table lay the reason for their sleepless night, a single steel shell fragment no larger than a man's thumb, recovered from a downed American anti-aircraft shell that had detonated in the air above Dortmund 2 weeks earlier. It was part of a fuse, but unlike anything the Reich's best engineers had ever seen. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. Dr. Kurt Diebner, once a physicist on Germany's own atomic project, leaned close to examine the tiny glass and copper components revealed by careful filing. "Das ist kein normaler Zünder," he muttered. "This is no ordinary fuse." Through the magnifying glass he saw miniature coils, a vacuum-sealed tube scarcely the width of a cigarette, and beneath it a fragile circuit board of astonishing compactness. The inscription on the copper base was stamped simply, VT Merc 45 Mod 2, US Navy. One of the assistants whispered, "Perhaps a radio proximity device?" Diebner did not answer. He knew enough about Allied reports to recognize that possibility. But what unsettled him was the craftsmanship. The soldering was immaculate, the layout deliberate, as if some unseen hand had rearranged the familiar laws of electronics into a new geometry of warfare. For 2 years, German air defense crews had reported a strange phenomenon over the Rhine and later over Saarde, the Ardennes shells that burst not on contact or timer, but seemingly at the perfect instant near their targets. Night fighters saw clouds of shrapnel detonate in synchronized blossoms, striking aircraft even when range estimations were wildly off. At first, these reports were dismissed as exaggeration or coincidence, but by the winter of 1944, the statistics could no longer be ignored. Luftwaffe loss rates to anti-aircraft fire had doubled in some sectors. V-1 flying bombs launched toward London were intercepted in mid-flight by gunfire that seemed preternaturally accurate. Somewhere, the Allies had mastered a weapon that measured distance without human error. The notion of a radio fuse was not new. German scientists at Telefunken and Siemens had experimented since 1939 with electronic triggers that could detect reflected signals from nearby metal objects. They had built prototypes using small triode tubes operating at tens of megahertz, but the devices were too large, too fragile, and too inconsistent to survive the shock of artillery launch. By 1942, research funds were diverted to radar and jet propulsion, projects promising immediate results. The idea of a functioning proximity fuse was quietly shelved. Now, under the light of the acetylene lamp, Diebner and his colleagues stared at proof that the impossible had been achieved and mass-produced. The irony struck him like a blow. The very industrial discipline Germany had once claimed as its pride, precision machining, meticulous calibration, had been outdone by the industrial democracy it mocked. To build such miniaturized electronics by the tens of millions required not genius alone, but an assembly line harmony of science and industry that totalitarian control could never match. He imagined the American factories, rows of women winding microscopic coils under magnifiers, automatic soldering baths, quality inspectors with stopwatches. Here in Germany, they still hand-built each prototype under siege, short of copper wire and vacuum tubes. Outside, the winter wind carried the distant rumble of artillery closer. Inside, Diebner's assistant held up the recovered fuse fragment beside a German electronic component for comparison. The contrast was humiliating. The American vacuum tube measured scarcely half the size, yet contained double the circuitry. Its glass envelope was flawless, its cathode precisely centered. Even with the Reich's best glass-blowing and metallurgy, reproducing such a device would take months' time the collapsing front would never allow. When the team finally traced the circuit and realized it operated as a miniature radio transmitter that sensed its own echo from a target, the room fell silent. Someone whispered, "5 Jahre, Mindestens, 5 years at least the gap, separating them from that level of practical electronics. Through the rest of that January night, they documented every component in meticulous sketches. The design used rugged epoxy insulation and a clever self-arming delay activated by the acceleration of firing features that showed deep understanding of both physics and battlefield conditions. Unlike German theoretical models that failed in testing, this device had survived a launch of more than 20,000 G-forces and still functioned reliably in flight. The engineers realized they were looking at the embodiment of an idea Germany had abandoned as premature. By dawn, their laboratory notebooks told a story of industrial evolution rather than espionage. The Allies had not stolen a German concept, they had simply advanced beyond it through relentless iteration and resources. When the first Soviet shells began landing near Kummersdorf that week, the team burned their notes to prevent capture. But the memory of that night of staring into the copper heart of a device that rendered German gunners obsolete would remain with those who survived. For them, the proximity fuse was not merely a technical marvel, it was a revelation of how far their nation had fallen behind while boasting of superiority. When word of the Kummersdorf discovery reached Berlin, it did not travel through the usual military channels. By early February 1945, the Reich's scientific offices had fractured into desperate enclaves, each protecting its own research, each convinced it could still deliver a miracle weapon in time. Yet even amid the chaos, a report stamped "Dringend, Hochgeheim" found its way to the Technisches Amt of the Luftwaffe. The subject line read simply, "Funknachrichtensender, amerikanischer Ursprung." General Wolfgang Martini, the Luftwaffe's chief radar officer, received the memo in his underground office beneath a bombed-out suburb of Berlin. Martini had seen Allied radar systems before fragments from downed bombers, the cavity magnetron that had stunned his technicians at Rechlin, the pulse equipment that had made night raids invisible. But this was different. A fuse so small it fit into an artillery shell, yet so advanced it could detect a moving aircraft that was something no German radar physicist had believed possible. He summoned his remaining engineers, men who had once worked on the Würzburg and Freya radars. As they unrolled the Kummersdorf sketches, the realization spread slowly across the room. The circuit did not rely on any exotic principle. It used the same radio reflection physics they themselves had studied before the war. The difference lay in execution, miniaturization, reliability, and sheer volume. One engineer estimated aloud, "To make such a fuse, you must have tens of thousands of identical vacuum tubes, each perfect, not handmade machine-produced." Martini nodded grimly, and to fit it inside a shell, they must have factories turning out micro-components by the million. Precision assembly lines, perhaps women or even automatic machines. Someone whispered, "Das ist Amerika, that is America." For the first time, the myth of German technical supremacy cracked completely. The Reich had invented many of the ideas: jet propulsion, guided missiles, early television, magnetic tape, yet had never learned to mass-produce them. The Americans, by contrast, had turned every concept into an industry. The proximity fuse was not a single invention. It was the visible tip of an invisible empire of factories, laboratories, and logistics. Captured Allied reports later confirmed what the Germans only suspected. Since 1942, under the U.S. Office of Scientific Research and Development, scientists at Johns Hopkins Applied Physics Laboratory had refined the fuse through thousands of live-fire tests. The British had first proposed it, but it was American industrial capacity that brought it to life. RCA, Western Electric, General Electric, and dozens of subcontractors coordinated to produce more than 20 million units by 1945. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now, back to the story. Each fuse was a triumph of automated precision. A vacuum tube 1 inch high, evacuated, sealed, and tested by machine. A battery that activated only under the acceleration of firing. A radar oscillator tuned to a few hundred megahertz, sensing target reflection through Doppler shift. The device could sense a wing or fuselage passing within 50 feet and detonate instantly, creating a sphere of lethal shrapnel that made conventional timing irrelevant. To the German analysts, the implications were staggering. Their own anti-aircraft shells, even when fired in dense flak barrages, depended on human gunners setting mechanical timers. Each timer had to be calibrated, each shell a guess. With VT fuses, American and British guns no longer guessed, they calculated. Wherever a bomber flew, the shells seemed to think for themselves. By spring of 1945, reports filtered in from the Western Front, confirming the devastation these fuses had wrought. German pilots over the Ardennes described flak that exploded, as if guided by radar. V-1 flying bombs, once confident in their speed, were now swatted from the sky by proximity-fused guns ringing London. And at sea, Japan's kamikaze raids were met by US Navy batteries using the same technology shells that burst precisely beside onrushing aircraft, often destroying them before impact. When German naval attachés in Tokyo relayed those results back to Berlin, the reaction was disbelief. Unmöglich, one admiral said impossible. But the impossible was now measurable in every burned-out hangar and every wrecked fighter that never made it home. In the war's final weeks, a handful of surviving German scientists, men from Siemens, Telefunken, and the Navy's Versuchanstalt, attempted a last reconstruction. They scavenged components from abandoned radar stations, hoping to replicate the American circuit. But with power shortages, scarce copper, and no industrial base left, their efforts were symbolic. The Reich could barely produce rifles, let alone micro-vacuum tubes. On April 10th, as Allied forces crossed the Elbe, Martini ordered the last remaining technical archives sealed or destroyed. He is said to have told a colleague, "If we had their factories, perhaps this war would have ended differently. But factories are built with freedom, not fear." Those who survived the collapse later spoke of that fuse as the moment the scientific war was truly lost, not to superior ideas, but to superior systems. Germany had built rockets to reach the stratosphere, but America had built factories that reached perfection. In the silence of defeat, that difference was undeniable. When Allied technical teams later found the abandoned sketches at Kummersdorf, they recognized the handwriting precise, weary, and resigned. A German engineer had scribbled a final line at the bottom of the page: "Ein Wunder, aber kein Wunderwaffe." A miracle, but not a miracle weapon. The war ended not with a bang for them, but with the scrape of boots and the creak of truck doors. In the first days of May 1945, as Soviet columns closed around Berlin, the remnants of the Kummersdorf research group surrendered to advancing American units near Nordhausen. They were engineers, not soldiers, men with hands calloused by solder and glass, clutching notebooks that no longer mattered. When interrogated by Allied technical officers, they expected punishment. Instead, the Americans asked questions patient, precise, and surprisingly respectful. They were taken to an improvised camp where tables overflowed with confiscated drawings, radar parts, and captured files. On one of those tables lay a box of pristine proximity fuses, fresh from American depots. For the first time, the Germans could see an intact example, not a fragment, but the finished artifact. Dr. Kurt Diebner lifted one in his palm. It weighed almost nothing. The clear glass revealed its delicate circuitry, the tiny copper coils glinting under fluorescent light. He turned it slowly, remembering the long night under the acetylene lamp at Kummersdorf. Everything he had suspected was now before him, perfect and whole, the final expression of a scientific world that had moved on without him. An American major noticed his silence. "Hell of a thing, isn't it?" he said. "We made 20 million of these. They kept the boys alive over the Pacific." Diebner nodded. In that moment he understood something deeper than defeat. It wasn't only that Germany had lost the war, it was that the future no longer belonged to nations that worshipped secrecy and genius. It belonged to those who could coordinate thousands of minds toward one practical miracle after another. That summer, the Americans began selecting scientists for relocation. Under the codename Operation Paperclip, dozens of physicists, chemists, and engineers were quietly transported to U.S. research centers Huntsville, White Sands, Dayton, Some came willingly, others reluctantly, but all came face to face with the industrial civilization that had overwhelmed them. In laboratories at Wright Field and the Naval Research Laboratory, former German radar specialists were shown new American devices that had evolved from the wartime fuse. Miniaturized transmitters, radar proximity detectors for rockets, early computers that automated targeting. Each innovation traced a lineage back to that single fuse, the seed from which post-war electronics would grow. One of the Germans, a quiet Telefunken engineer named Hans Ernst, later wrote in a private letter, "In Berlin, we built machines to command men. In America, they built machines to serve them. That is why their science endured." The proximity fuse had begun as a battlefield secret, yet by 1950 it had become a classroom example of applied physics and manufacturing. Its principles lived on in guided missiles, satellites, and the very heart of Cold War deterrence. For the men who had once dissected it under flickering lamps, the sight of those new devices was both awe and regret intertwined. By the early 1950s, when Germany lay divided and reconstruction began, a few of those scientists found work again in civil electronics, radio, and television. They built transmitters that carried music instead of orders, circuits that illuminated homes instead of battlefields. Yet the memory of that small glass fuse remained. Some kept fragments of it, a piece of copper coil, a section of glass envelope as a private reminder of what true progress required. When Diebner was asked, years later during an interview, what invention had most impressed him during the war, he did not mention rockets or jets. He paused, adjusted his spectacles, and said quietly, "A fuse. Because it taught us that precision is not the privilege of genius, it is the product of freedom." The interviewer thought he was being poetic, but those who had lived through Kummersdorf understood. In that tiny vacuum tube lay the moral of the 20th century, that the wars of engineers are not won by ideas alone, but by the societies capable of turning ideas into reality. And so the story ended not in triumph or tragedy, but in understanding. A handful of men who once worked by the light of burning cities would spend the rest of their lives under electric lamps powered by the very industry that had defeated them. They had seen the future up close, through the fragile glass of a proximity fuse, and it had been American-made. The night train from Frankfurt to Munich cut through the ruined landscape of post-war Germany like a scar healing in motion. Outside the window, blackened towns flickered past factories roofless and hollow, chimneys standing like gravestones. Inside the carriage, a handful of passengers dozed under army blankets. Among them sat Hans Ernst, once an engineer at Telefunken's radar division, now a civilian consultant for a new company called Siemens Halske. In his briefcase lay something that, 5 years earlier, would have been unthinkable, a letter of invitation from the United States Army Signal Corps. It was 1949, and Germany was no longer a battlefield, it was a laboratory again. The Americans had stayed. Their occupation had hardened into administration, and then into partnership. Where once Allied officers had confiscated every oscilloscope and radio part, they now funded new workshops under Marshall Plan reconstruction loans. Ernst could scarcely believe the reversal. In a few short years, the same laboratories that had once fueled the Luftwaffe's technological ambitions were now subsidized by the very power they had tried to destroy. At Siemens, the work was no longer secret. Engineers built radar beacons for civil aviation, weather transmitters, and radio navigation aids. And with every new project, Ernst felt an echo of that night at Kummersdorf. He saw it in the compact radio circuits, in the vacuum tubes now made smaller and cheaper than ever. He recognized the same principles that had once amazed him inside the captured American fuse: miniaturization, modular design, reliability through standardization. The Americans had called it production engineering. To Ernst, it was a philosophy of freedom in metal and glass. By 1950, the US had invited dozens of German specialists to consult on radar and missile projects. Some went under Operation Paperclip, others as civilians. The names were scattered across continents now: von Braun in Alabama, Martini advising in Dayton, Diebner quietly lecturing in Göttingen under a new democratic university charter. They had all survived the same revelation. that science divorced from conscience breeds only ashes. When Ernst arrived in Washington, he was escorted not to a laboratory but to a factory, the Radio Corporation of America's plant in Camden, New Jersey. The manager, a cheerful man with a tie too bright for wartime Europe, led him through long aisles where hundreds of women worked in silence. At each station, a worker assembled a single step of an electronic component, coiling wire, inserting it into a socket, sealing it with glass. The rhythm was hypnotic, an orchestra of precision without a conductor. "This," said the manager proudly, "is where we made the VT fuse. Every part tested, every 10th unit destroyed to verify quality. We still make about 10,000 tubes a day, only now they go into televisions." Televisions. The word hit Ernst like a paradox. The same circuits that once calculated death above Europe now carried moving pictures of baseball and comedy shows. He felt both admiration and guilt. How easily technology had changed purpose, as if morality itself were a matter of rewiring. He realized that America had achieved something far beyond technical mastery. It had turned production into philosophy. In Germany, perfection had been an end in itself, the proof of genius. In America, perfection was the byproduct of practicality. 1,000 small improvements, each by ordinary hands, could accomplish what no single visionary ever could. Later that year, during a symposium at MIT, an American engineer joked, "The proximity fuse wasn't a secret weapon, it was a manufacturing miracle that just happened to explode." The room laughed, but to the Germans in attendance, the humor carried the sting of truth. By the mid-1950 seconds, the world divided itself again. Two superpowers now faced each other not across trenches, but across equations. Every advance in radar, rocketry, and nuclear physics was shadowed by its opposite number beyond the Iron Curtain. At Wright-Patterson Air Force Base, Dr. Wolfgang Martini, the former Luftwaffe radar chief, worked quietly under contract as a consultant. His reports were now written in English, his equations typed on American stationery. He was respected, even well paid, yet he often felt like a ghost haunting the future he had failed to create. One day, a young American lieutenant showed him a new device, a transistorized proximity detector, barely the size of a matchbox. It was solid state, no fragile vacuum tubes at all. Martini turned it over in his hand, his eyes widening as he recognized its lineage. "This," he murmured, "is the child of that fuse." The lieutenant smiled. "Yes, sir, and its grandchildren will guide missiles and satellites." The transistor, born in 1947 at Bell Labs, had rendered entire wartime technologies obsolete within a decade, but a conceptual ancestor was clear: the wartime race for miniaturization that began with the need to fit radar into an artillery shell. The proximity fuse, in its way, had launched the electronic age. To the German scientists, that knowledge was bittersweet. They had touched the origins of something vast, but too soon, and in service of the wrong cause. Meanwhile, across the Atlantic, their former colleague Wernher von Braun had turned rockets into instruments of exploration. At Redstone Arsenal in Alabama, he led a team of German engineers under the American flag, building the missiles that would soon reach space. When Sputnik shocked the world in 1957, von Braun's group was ready with a response. Explorer 1, America's first satellite. Its telemetry and trigger systems, derived from high-altitude fusing circuits, cousins of the VT mechanism that once terrified Luftwaffe pilots. The irony was complete. The weapon that symbolized industrial death had evolved into the technology that measured cosmic life. The same principles that once guided flak bursts now guided spacecraft through orbit. When the Germans met again at a scientific congress in 1958, they were older, greyer, quieter. Some worked for NATO, others for civilian research institutes. Deibner, the physicist who had first examined the captured fuse, presented a paper on semiconductor behavior under high acceleration, a purely technical subject, yet his closing words broke from mathematics. "During the war," he said, "we thought precision was a matter of skill. We learned too late that it was a matter of cooperation. No single mind builds a proximity fuse, nor a rocket, nor peace. Only a society can." The audience applauded politely, not realizing they were hearing the confession of an entire generation. In 1960, on the 15th anniversary of Germany's surrender, Ernst visited the ruins of Kummersdorf for the first time. The site was overgrown with birch and pine. Concrete bunkers lay collapsed, their entrances filled with leaves. He found the remnants of the old laboratory, the same one where he and Diebner had once examined the captured fuse under flickering lamps. On the floor, buried under dirt, lay the rusted ring of a fuse casing German, not American. He picked it up and turned it in his hand. For a moment, the sound of distant artillery seemed to echo again in the wind, but the world had moved on. Somewhere above him, a U. Reconnaissance satellites circled the planet, its sensors and radio triggers descendants of that long-ago discovery. The sky that once delivered destruction now delivered data. He felt no bitterness, only clarity. Technology had never belonged to nations. It belonged to methods. The Allies had won because their methods multiplied. And in that multiplication lay the seed of a civilization that could rebuild even its enemies. In the early 1962, West Germany began re-entering the scientific world as a partner. The new Federal Republic sent delegations to CERN, to NATO, to transatlantic research projects. A younger generation of engineers, students who had never known the sound of bombers, filled the universities. They learned about radar, electronics, and automation, not as instruments of war, but as tools of communication and medicine. Diebner, by then in his 60s, lectured occasionally at Göttingen. One evening after class, a student asked him what it had felt like to work on military technology under the Reich. He paused for a long time before answering. "It felt," he said slowly, "like painting in the dark. You think you're creating form, but only later you see what you've built. Science is blind without purpose. The Americans taught me that purpose can be practical and humane." The student nodded, uncertain. To her, the war was a story in black and white films, not the living scar it remained for her professor. She could not imagine a world where knowledge itself felt dangerous. By 1965, the transistor had evolved into the integrated circuit, a microchip smaller than a postage stamp, containing thousands of electronic pathways. When Ernst visited an exhibition in Hanover that year, he saw a small display titled "From Vacuum Tube to Microchip: The History of Miniaturization." Behind glass sat the entire lineage of 20th century electronics. A crude triode from the 1922, a proximity fuse vacuum tube from 1944, a transistor from 1955, and finally a silicon chip gleaming under fluorescent light. Visitors admired the modern chip, barely glancing at the wartime relic beside it. But to Ernst, that small cylindrical fuse was the keystone of the entire story. He realized that within it lay the DNA of everything that followed: radar, computers, satellites, even the devices that now filled living rooms and hospitals. It struck him then that progress was cumulative, not because of genius, but because of memory. Each generation built upon the preserved effort of the last, whether in peace or in war. The proximity fuse had been conceived to destroy, yet its descendants now enabled communication and exploration. That paradox, he thought, was humanity itself, forever transforming danger into discovery. In 1968, when Diebner died quietly at his home, a former American colleague sent a letter of condolence. It contained a single line: he was one of the few who saw how science defeated ideology. At his funeral, among the sparse attendees, Ernst laid a small brass ring, the fragment of the fuse he had kept since Kummersdorf, beside the coffin. No speech was given, only silence. But in that silence lay the full circle of their journey, from fear to understanding, from secret laboratories to open universities. Afterward, as he walked home through the rebuilt streets of Göttingen, he passed a store window displaying the newest marvel, a compact transistor radio, advertised as "Made in West Germany." He smiled faintly. The country that once waged war for technical supremacy was now selling peace through precision. He thought of the American major's words 2 decades earlier: "We made 20 million of these. they kept the boys alive. How strange that survival, too, could be mass-produced. By the end of the 1960 seconds, the world was preparing to leave the Earth. The Apollo missions carried computers that operated on circuits tracing their ancestry back to that wartime innovation. Their guidance systems, their timing relays, their fail-safe triggers, all were descendants of the same design logic first proven in a fuse above the skies of Europe. When humanity finally set foot on the moon in 1969, it did so on the shoulders of countless invisible engineers, including those who had once stared in awe at an American device on a German workbench. Historians would later write volumes about the atomic bomb and the jet engine, but few remembered the proximity fuse. It had no dramatic unveiling, no mushroom cloud, no photograph of surrender. It worked invisibly, faithfully, and perfectly, a quiet revolution that rewrote the mathematics of warfare. And in doing so, it reshaped the world's understanding of what was possible. For the men of Kummersdorf, that was enough. They had witnessed the birth of precision itself, not as an abstract virtue, but as the defining rhythm of the modern world. In his final years, Hans Ernst often walked by the university's electronics lab, watching students solder circuits onto printed boards. They spoke in English and German interchangeably, their minds unburdened by borders. He once stopped to help a student struggling with an oscillating circuit. With practiced hands, he adjusted a capacitor, watched the waveform stabilize, and smiled. "There," he said softly, "stable like a fuse that knows its distance." The student laughed, unaware of the weight behind the words. That night, Ernst wrote in his diary, "Perhaps the true victory of science is not invention, but forgiveness when the tools once built for destruction become instruments of progress." He died a few years later, his notebooks donated to the Technical Museum in Munich. Among the items was a single preserved artifact, an American VT fuse, perfectly intact. The curator placed it in a glass case beside early transistors and radar tubes. Few visitors paused to look at it, but those who did could read the small plaque beneath. Recovered in Germany, 1945, the fuse that changed the mathematics of war and the future of technology. By the late 1970s, the laboratories of Europe no longer smelled of ozone and cordite, but of solder and silicon. A new generation of engineers, born after the war, worked in bright, glass-walled offices, filled with the hum of fluorescent lights. They spoke of data transmission, automation, and integrated logic, not weapons. Yet, unknowingly, they carried the inheritance of that long-ago discovery. When the first microprocessors appeared, chips containing thousands of transistors, a quiet recognition passed among the few surviving veterans of the old radar laboratories. This was the final distillation of the wartime fuse, a thinking circuit small enough to fit in the palm of one's hand. What had once been designed to detonate now calculated, measured, and stored memory. Hans Ernst would have been proud, though he did not live to see it. His students, many of them now professors, occasionally mentioned his strange fascination with the American distance trigger. They never realized that, to him, it symbolized the precise moment when science crossed from arrogance to humility. In the archives of the Munich Technical Museum, the brass-bodied fuse remains sealed in its display case. Dust gathers slowly on the glass. Tourists walk past, drawn instead to the sleek jet engines and rockets nearby. Yet every so often, an old man pauses before it, a veteran, perhaps, or a retired engineer, and stands silently for a long moment. Because that fuse was more than a weapon. It was a mirror, one that reflected the cost of brilliance without conscience, and the redemption that came when knowledge was finally shared rather than hoarded. It was proof that civilization could rebuild not just its cities, but its ethics. The modern world, with its satellites, smart sensors, and computers, owes its quiet efficiency to that invisible transformation that began in the wreckage of 1944. In its circuitry lives the memory of precision, the belief that progress, once unleashed, cannot belong to war alone. And so, the story ends where it began, with a small device, humming silently, measuring distance. But now, instead of gauging how near death lies, It measures how far humanity has come. Up next, you've got 2 more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.